To deal with this lesson oscillations, in which the first topic is periodic motion. Any motion that repeats itself in regular intervals of time is called periodic motion, such as you can say examples of it: heartbeat which repeats itself in regular interval of time, and you can talk about an earth revolving around the sun. It gets repeated itself 365 days, so that's periodic. So these are the good examples of periodic motion, any motion which repeats itself in regular intervals of time. So next is, what is oscillatory or harmonic motion? Okay, oscillatory motion is also called harmonic, or even you can call it a simple harmonic motion. Okay, simple harmonic motion. What is oscillatory motion? Any motion in which the particles are vibrating to and fro about the mean position. Take a pendulum for that matter. It's going to oscillate to and fro about the mean position. This is the mean position. This is called the extreme position. So then the particle moves to and fro about the mean position. Due to it is getting back to the mean position because of the restoring force. Such a motion is called oscillatory motion. So oscillatory motion, if a body moves back and forth repeatedly about the mean position, its motion is said to be oscillatory or simple harmonic, where it involves a restoring force which brings back the body to the mean position. Okay, that's what is known as oscillatory or simple harmonic motion. A swinging of the pendulum is example. So a pendulum is one example. A bob, mass of the bob suspended by means of spring, or even a normal spring, when you pull it to the right, it will experience restoring force. It tends to oscillate to and fro about the mean position. So these are the examples. The vibration of a string in guitar, it vibrates to and fro about the mean position. So these are the examples of simple harmonic or oscillatory. So you notice that every oscillatory motion will be periodic, but every periodic motion will not be oscillatory, because for oscillatory it has to vibrate to and fro about the mean position. In a periodic motion you don't have anything called a mean position, just rotating about with this as the center. There is no to and fro movement. So that is the basic difference between a periodic motion and an oscillatory motion. So let's talk about Fourier analysis. Fourier said that any sine function or a cos function, any sine function or a cos function will repeat itself periodically. A sine function is sine 0 0, so it goes like this, and a cos function cos 0 is 1, so it goes like this. They repeat itself and they also move to and fro about the mean position. And so they can be classified as a simple harmonic motion. So Fourier said that it will also be periodic, it will also be simple harmonic. Okay, so then that's what it is. So if you take this function f of t, which is sine function, which is sine omega t, where if you want to see it's periodic, you write sine omega t plus capital T, and omega itself is 2 pi by capital T into t plus capital T. Take it inside, sine 2 pi small t by capital T plus just 2 pi when you take it inside, and a 2 pi plus will be in the first quadrant in trigonometry. A 2 pi is here and plus will be in the first quadrant where all is positive, and it's also an even integral. Therefore it will remain to be sine 2 pi t by capital T, which is nothing but sine omega t. The function remains unchanged even though I added a time period capital T to it. I am retaining the same function, so then therefore this is a periodic function, and it's also simple harmonic in nature. So then the coefficients, and these sine functions can also have coefficient a or b. It can be any number multiplied to it, so that's fine. Then you can term it as a simple harmonic function. But it can't be with a 1 plus sine omega t. That 1 will not make it simple harmonic. It will only be periodic in nature, but not be simple harmonic. Any simple harmonic function should be of the form a sine omega t or a b cos omega t or 2 omega t or 3, anywhere, anything is okay. It should be represented as one single or one single sine or a cos function. Okay, but when you have an a plus, see for example you have a plus b cos omega t, this will be periodic. It's an a is added, a constant is added, it will make it periodic, but it will not be simple harmonic. I hope you're clear with that. So that is the conclusion by Fourier. Okay, now let's look at some examples. Look at this. This is how a DC current is represented. An alternative current is like this, and a DC current is like this, direct current. Battery linde varudilla current, torch battery portal, that is a DC current. It is represented like this. Can you see it's getting repeated at regular intervals of time? So it is periodic, but it is not simple harmonic. Similarly, look at this. Similarly, the digital pulse. These are all periodic, but they are not simple harmonic because they are not represented as a sine function or a cos function. It has to be necessarily a sine or cos to make it simple harmonic. I am sure you understood. Then we did a sum here where they said a human heart is found to beat 75 times in a minute. When they say 1 minute, we write it as 75 times in 60 seconds. Therefore, 1 second, how many times will it beat? So x will be 75 by 60. 15 5 is 75, 15 4. So 5 by 4 will be the frequency. The frequency is 5 by 4. Therefore, you understand frequency is the number of beats per second. Number of beats per second in case of the heartbeat, or number of oscillations per second. Number of oscillations per second is what is called frequency. So thus you know how to define frequency. Let's define what is amplitude. Amplitude means in the case of vibrating body which is vibrating to and fro about the mean position, the maximum displacement from the mean position is what is called amplitude. The particle is vibrating to and fro, the maximum displacement from the mean position is what is called A. The same wave, a sine wave, this is a sine wave which can also be represented as a rotational motion because it's sine 0 is 0. Sine 90 is 1 and this is 90. This is pi and which comes here. This is pi by 2, pi 3 pi by 2. Can you see? This is called a phasor diagram. A phasor diagram. And this is called the wave, sine wave or cos wave. You can represent it like this or also like this. It's all the same. So therefore, here in the rotational motion, this radius is what stands for amplitude because O is considered to be the mean position. So when a particle is vibrating, it vibrates from to and fro about the mean position. So as it goes on, when the particle is here, it gets projected on the circle like this. So the particle is here, it gets projected here. Particle is here, it gets projected here. So then it's represented as a rotational motion. I hope you understood that point. So then this is what is an amplitude? Amplitude is the maximum displacement about the mean position. And what is frequency? Is the number of oscillations per unit second. What is time period? Time period is the reciprocal of frequency. And frequency is SI unit is hertz. You know it from 10th standard sound lesson, but that was omitted for you. But just get to know frequency is SI unit is hertz, which is per second is hertz, and time period is second, which is a reciprocal of frequency. So what is time period? Time taken for one complete oscillation. Time period, capital T, is the time taken for one complete oscillation. So you must learn all these terms. What is frequency? What is amplitude? What is time period? These are the key things that you have to learn. So next thing that I taught is a numerical where there was a sin omega t plus cos omega t. You have to see that it's periodic. And from Fourier analysis it is periodic, but still you can write that take what is here omega. And therefore, omega is equal to 2 pi by capital T. So time period of this is also 2 pi by omega. The time period of this is also 2 pi by omega. So they will repeat itself at regular intervals of time T. Therefore, they both are together, put together, they are definitely periodic in nature. But they'll ask you to find it is simple harmonic. How do you do that? You have to make sure that you have to represent it as one single function. Let's take sin omega t plus cos omega t. In this case, multiply and divide by root 2. Take the root 2 in the denominator alone inside. So, you will get 1 by root 2 sin omega t plus 1 by root 2 cos omega t. And you can represent this as 1 by root 2 as cos 45 sin omega t plus this as sin 45 cos omega t. So, it's like cos A sin A cos B plus cos A sin B, which is nothing but sin of A plus B. Sin of omega t plus 45 degrees pi by 4. Thus it's become like a Fourier theorem where root 2 is there. There is no plus 1 or anything. So therefore it's not only periodic, it is also simple harmonic in nature. So that's, you can conclude that it's periodic as well as simple harmonic. Every simple harmonic is periodic. So there's no need to say periodic once you say simple harmonic. So let's go to next question. Exponential function. They are asking, is exponential function a simple harmonic function? An exponential function is simply like this, an ordinary exponential function. And this is the reciprocal of an exponential function. So then therefore, see, exponential functions graph is like this. Okay, it will go like that. Though I am showing only this part, it goes like this. And a reciprocal function will go like this. Just the mirror image of it to the left side. So this is what is exponential functions. Reciprocal is the green graph. So because of the negative sign, and you know they are definitely not repeating itself, though it's not periodic, and definitely not simple harmonic also. So that's done because only a periodic function can be tested for even simple harmonics. So let's go to next question. Oh, logarithmic function. The next question here is log graph, and the log graph, the log of omega t. Okay. So let's see how a logarithm graph looks like. It's going to be something like this. So then therefore it is not periodic, it's not repeating itself. That shows that it's simply not repeating itself. So that's done. And next thing, next sum that I would like to go through in Aurora is this: a sum sin pi t plus 2 cos 2 pi t plus 3 sin 3 pi t. This is the sum. Okay, what is in the place of omega? You have pi, and omega is equal to 2 pi by capital T, which is equated to pi here, and pi get cancelled. So from here t is equal to 2 seconds. What is omega? 2 pi here, but omega itself is 2 pi by capital T is equal to 2 pi, so t is equal to 1 second. Here what is omega? 3 pi. Omega itself is 2 pi by capital T, which is equal to 3 pi here, and pi gets cancelled. T is equal to 2 by 3. Therefore, you understand this is taken as capital T. This time period will be T by 2 because it's 1 second. And this will be 1/3 T by 3. Therefore, in the bell 3 times ring பண்ணும்போது, third time ring பண்ணும்போது, it will collide with this. And this when the second time ring பண்ணும்போது, it will. So then therefore, it's like an LCM. And so it's repeating itself in regular intervals of time T. All of the three of them together. Therefore, when you add up, it will be a periodic function with the time period as 2 seconds. Time period as 2 seconds. So it is definitely periodic. But can you say it's simple harmonic? Can you express this as one single sign function? You cannot. Therefore, because there are 3 terms, the multiplying, dividing by root 2 and all will not help in this. So then therefore, it is only periodic, but it's not simple harmonic. I hope you understood. So the next thing that I have to teach you is how to depict. Okay, I should talk to you about spring. Okay, the one example of a simple harmonic motion is the spring. You know, when you pull the spring to the right, it will leave it. It will tend to oscillate to and fro about the mean position. The center position, the mean position is when there is no force applied. It's in equilibrium. The moment you pull it to the right, it will start oscillating to and fro about the mean position. It's called simple harmonic motion, where you know that the force is the restoring force, which is always opposing the displacement x. The restoring force opposes the displacement x, and so F is proportional to x. F is equal to minus k into x, where k is a spring constant of different material. You already know F is equal to m into A. So then therefore equating 1 and equating 2, you get MA is equal to minus kx. So A is equal to minus k by m into x. And this becomes your equation 3. Let me now show you how to depict a particle in a rotational motion, a circular motion. In a uniform circular motion, how to do displacement. How to depict displacement in simple harmonic motion. Okay, as a uniform circular motion. How to depict displacement in simple harmonic motion. And you have to draw this phasor diagram, a circular diagram, where there is point P. That A, or let's call it as A. Let A be the initial point, which already makes an angle omega t with the positive x-axis. The omega t is already existing angle with the positive x-axis. Now it's going to make an additional angle of phi naught. So this is at a time t is equal to 0, and this is at a time t. So with the time t, it's moved from here to here, making an angle phi naught. The total angle that the final position makes with the x-axis, therefore, is omega t plus phi naught. Okay, the total angle. You're going to make it, project this particle on the x-axis, because the particle is anyway going to move to and fro about the mean position. To move to that position only in this direction, this is what is called x. So this is called x. Take this triangle. You know that radius is nothing but your amplitude. Did I say that before? Yes. So you know the radius will be amplitude. And so taking this triangle, you know cos omega t plus phi naught. It will be adjacent by hypotenuse, which is x by a. Therefore, x itself is a cos omega t plus phi naught. Thus, this is how in a rotational motion you get what a displacement vector is. Okay, so thus you got a displacement. Now, if you differentiate this itself, we'll get velocity. How to differentiate this is v is equal to dx by dt. And I told you a cos of anything is minus sign. Okay, so and then you have to differentiate the inner part of it. So it will become minus a omega sin omega t plus phi naught. Now if you want acceleration, you have to differentiate this again, which will be d square x by dt square. Not dx by dt the whole square. No. That's not double differentiation. It's d square x by dt square. So when you differentiate a sign, you'll get a cos. You know, sign of anything is just a cos of that thing, but you have to differentiate the inner of it. So you'll get the minus a omega square will become, one more omega will get multiplied, cos of omega t plus phi naught. From this equation, you know a cos omega t plus phi naught can be written as x. So substituting that, you get minus a cos omega t plus phi naught is x. So minus omega square x. This is my equation 4. Comparing this equation 3 and this equation 4, you understand omega square is equal to k by m. Omega is equal to root of k by m. And you know time period is equal to 2 pi into root of, okay, time period is omega is equal to 2 pi by capital T. T is equal to 2 pi by omega. So T is equal to 2 pi by omega, when you substitute, it will become root of m by k. Because when you divide the time period, when you divide the 2 pi by omega, omega is root of k by m, it will go up m by k. Remember, m has to come at the top. 2 pi, this is the time period. These formulas you must memorize. Now, we got this as velocity, right? They'll ask you to depict and get this formula by drawing rotational motion, circular motion. If the question is about by drawing, not differentiating, then you should go for, this is the point, final point P, which is making an angle omega t plus phi naught. You know the velocity vector is always tangential to the circular motion, and linear velocity is r times angular velocity, which will be a omega here. You just extend this and make sure that the particle is moving from P dash to Q dash. Then the particle would have also moved from P to Q, and P dash Q dash is equal to PQ. You know, if this is cos omega t plus phi naught, this by similarity will be cos omega t plus phi naught is the angle. Sorry, not cos, just omega t plus phi naught. Taking this triangle, if you want to find PQ, which is on the opposite side, which is eventually P dash Q dash, you have to use sine. So sine omega t plus phi naught is equal to opposite, which is PQ. By hypotenuse, in this triangle, the hypotenuse is a omega. Therefore, PQ itself is a omega sine omega t plus phi naught. However, this is directed towards the velocity is directed towards the center. It's moved from P dash to Q dash in this case. So then therefore you have to insert a negative sign, which is also equal to P dash Q dash, and that gives you P dash Q dash vector, which is velocity vector, is minus a omega sine omega t plus phi naught. Thus you get the velocity here, and which is the same as what you wrote by differentiating also. So what you got by differentiating is what you get by depicting the diagram also. That clarity you should have. From here, you know, you can write v is equal to minus a omega root of 1 minus cos square omega t plus phi naught. And cos omega t plus phi naught, according to the first phasor diagram, is x by a. So substituting minus a omega into root of 1 minus x square by a square. When you take LCM, a and a will get cancelled. Minus omega root of a square minus x square will be the velocities formula. You should memorize it. You know, velocity at the mean position. What is the meaning of mean position? The center position, x will be 0. You substitute x as 0, the velocity at the mean position will be maximum velocity, which is minus omega into a. At extreme position, you know, x will be plus or minus a. X ku bala the substitute panna, you get v will be 0. That shows that v is minimum at the extreme position. So when a pendulum is in the extreme position or spring is at the extreme position, velocity is 0. So kinetic energy will also be 0. The potential energy will be maximum. When it is the mean position, you understand the velocity is maximum. So kinetic energy will be maximum, but the potential energy will be 0. These are the basic things that you have to know. And you know, when the pendulum is going towards the right, the acceleration will be, it will be retarding. It will be retarding because it will try to bring it down to the center. So these are things you should generally know. So then next is how to depict acceleration. That is this formula. How do you get, we got it by differentiating, no? How do you get it by diagram? This formula, how do you get it by diagram? So just draw the circular motion. Mark this as P and this is making angle omega t plus phi naught. You know centripetal acceleration is always directed towards the center and AC is equal to V square by R by the first volume's portion and linear velocity is R times angular velocity. But R itself is here amplitude. So it's A square omega square by A. So it's A omega square. So then it's A, capital A into omega square is the centripetal acceleration. If you break this down into the horizontal component, that will be A omega square cos omega t plus phi naught. And you know the acceleration is also always directed towards the center. So then therefore it will be minus A omega square cos omega t will be the done, that you got whatever we need. So this is how you write it in the case of diagram. That is how you write using differentiation. So you should know how to represent by differentiation, by circular diagram. You must be clear with everything. Okay, so then the next thing that I forgot to tell you, if supposing they ask you, write a differential equation of simple harmonic motion. You already know how to write f is equal to minus kx, f is also equal to m into a. So ma is equal to minus kx, you know this, correct? But a is nothing but d square x by dt square is equal to minus kx. So d square x by dt square is equal to minus k by m into x. You already know k by m is nothing but omega. K by m is nothing but omega square. So minus omega square x. So d square x by dt square plus omega square x is equal to 0. And this will be the differential. If they ask you to write a differential equation, you can write it like this. You can also write it using a differentiation method. You know, you wrote it here. You see? You differentiated here. Can you see? You can still retain it as d square x by dt square and take the omega square x to the other side. So you still can get d square x by dt square plus omega square x is equal to 0. You can give them answers as by differentiating or without differentiating. You can write this and just write a differential equation. So this is how you arrive at a differential equation of a simple harmonic motion. So they simply say to find whether it's simple harmonic, you can also check whether A is proportional to minus x. A is proportional to minus x. If A is equal to minus x, you can call it as a simple harmonic motion. Another way of terming, this is the main way of terming simple harmonic, main condition to define simple harmonic motion, where the acceleration will be negative of the displacement, which means it is obviously bringing it towards the mean position. So this is what I have taken in the other class till now. So let's continue the second part next class.